farmer has 2,400 feet of fencing and wants to make a rectangular pen and border. This is not smart, so the picture is this. Here's a river, this part is river, and then he wants to build a pen looking like this. Of course, you don't want to keep any ducks in here because ducks can swim. No farmer really does that. Better, okay, I didn't write this question. I just copied off of a Algebra 1 book. Better question would be, this is a barn, this is a wall already existing, and then you build this kind of fencing to keep some chickens and stuff in, okay? So now this fencing material is 2,400 feet. Now, what would be the dimension to make this area maximum, okay? Algebra teachers, for some reason, oh yeah, this is like x, 2x plus y over here. How do you know what to do if you're in Algebra 1? So instead, I have this two-column approach, okay? So this is geometry algebra column, and this will be calculus column, okay? So I start with my function. A is equal to, and then let's see, width times length, right? Width times length is my function. At the moment, it looks like multivariable calculus, two variable functions. So, okay, that's no good, but are they really two independent variables? No, they are not. They are related somehow. So now I need to find the relationship using my geometry and algebra knowledge. So let's take a look at this situation. Looks like the entire fencing material, which is 2W and 1L, has to be 2,400, right? Looks like eliminating L. You have done this before, right? Eliminating L would be an easier way to do. Now you substitute it back here. So this is W times 2,400 minus 2W. Okay, at this point, we already know how to solve this because this is Algebra 1. This needs to be upside down parabola with the zeros at one of them here and the other one here. And your maximum will occur right there, halfway, wouldn't it? So we can easily do this, but I'm trying to teach you the process here. So, see, at the maximum, your derivative is 0. We are finding it's exactly the same thing. It's a max-min problem now, isn't it? So, let's take a derivative, but before we take a derivative, we'll distribute this to avoid the product rule. Okay, this is my A. Now I'm going to take the derivative, which is like that. Now find the critical point by setting this to 0 because this thing does not have any place where it's undefined. And then I will see this is same answer as before, right? Okay, now the common question is, do we have to figure out increasing, decreasing, that kind of stuff? And answer is no, because within the context of this problem, we are clearly looking for the not the local max, but absolute max, isn't it? So even if my function looks like this, for example, if I find all of the critical points, it will be this point and that point. And then, of course, endpoint comes into play. So instead of doing inequality and increasing, decreasing, it would be much easier to just compare the y values of all 4 of these candidates, right? So what are our candidates? Our candidate is this one right here. Oops, did not want it. This one right here. Or to endpoint. But obviously to endpoint will give you 0 if I plug in 0 here, or 1,200. So this is it. So this is my maximum, isn't it? Now, but we have to find the y value because it says the dimension. So y value using this thingy right here, that will give me 1,200 feet. And finally, max-min is always well, you have to figure out the value of the function. So multiply these two together, then, oh boy, 600 times, it's not going to recognize my handwriting this way, 1200 times 600, and using this OneNote to do the math. Okay, 720,000. How about that? Okay, so that's Algebra 1 problem done by using calculus. Now let's move on to pre-calculus type of problem, or Algebra 2. I think this problem was in your pre-calc book. So this time, 80 meters of fencing material, and then farmer wants to build this type of thing. Okay, equal area, and we want to maximize the overall area. Now, your pre-calc book did something very idiotic, something like this, and then, right? Oh, forget it. God, no. Why would you want to do such a thing, right? Instead of that, I just start with area is equal to width times length. So once again, this is width, and that whole thing is a length. Okay, make it simple. Let's keep it simple. Now, then we have a same situation. So let's find the relationship. Now I have 4 W's and 2 L's is equal to 80 now. Once again, we would like to eliminate L, so it's 40 minus 2W now, isn't it? And then you realize quickly, it's the exact same thing. So this is W and then 40 minus 2W. You see this look exactly same as before, and then automatically this thing pops up in the back of your eyeball, and zeros are one of them here and the other one is here. So maximum should be right there at 10. But let's pretend that our algebra skill is not that good, and we'll use calculus. To avoid the product rule again, I'm going to distribute, then take a derivative, and set it equal to 0. Now W is equal to 10, predictably. Now, once again, we are looking for absolute maximum, so we are comparing this critical point with 2 of the endpoint, and 2 of the endpoint will give us 0. So I will just use this one. This must be my maximum. Plug it in here, and you have 20. Similar ratio of dimensions, and your area, of course, is 200 square meters. This is my maximum. How about that? I didn't write the maximum here. Okay, now let's move on to something that is calculus worthy. Okay, now calculus worthy problem is this: area of the largest rectangle that can be inscribed in a semicircle with a radius r, and we don't even know what that radius. Yikes. Okay, I have graphics ready for you. So this semicircle is for some unknown radius r, and you should be able to animate your thing like this. So as you can see, area right here, it will reach a maximum at some point. This will be 0 at one extreme, that will be 0 at another extreme, but somewhere in the middle. See, it's increasing, 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 still increasing, and after that it goes back down. Looks like this is our maximum, isn't it? Somewhere there. Okay, now I'm gonna copy this to your note. Okay, now we have the picture. So there are 2 different ways to do this. Let's just set it up the same way we did before. So this area happens to be, this time I'm gonna call this thingy x that much, and y is that much. So your area is 2xy. Now you might say, why not call this thing length or x, right? Let's think about it. This is a coordinate plane, right? How about that? And more importantly, we need a relationship between x and y in order to avoid multivariable calculus. Now, if the radius of this is r, what would be the relationship between x and y? How do you like it? Right? Okay, so we can do the same thing and let's solve for y, which is, and substitute it here. And then this is a product rule from hell now, isn't it? And the chain, okay. I'm not doing that. Let's just sit back and think. Okay. Maybe we still know this is like x, y are not two independent variable. So can I just still just thinking y is a function of x and do an implicit derivative with respect to x? This is what I mean. Can I do that? Let's try and see what happens. So this becomes the a over the x, which is what we want. Now we have a product rule. So this part is your u, and that thing is your v. So product rule goes v prime, u prime v, and u v prime. Okay, so let's see how that goes. So u prime is 2 times y plus u 2x and v prime, derivative of y. Well, how about this, right? Well, then you might ask me, what is dy over dx? Where do we get it? We get it from here. Do you remember? Implicit derivative? Yeah, this thing comes in mighty handy now, doesn't it? So this thing is 2x plus this thing is 2y, and of course the chain rule. And r is constant, so it's not 2r, it is 0. So dy over dx then turns out to be negative x over y. Good. Now shove it right in here, okay? So what we have is 2y plus negative, right? So it becomes minus. And I already have 2x, so we have 2x squared over y. Okay, when do we plug in that y value, which is ugly square root of r squared minus x? Good things happen to those who wait. I'm going to common denominator this thing. Oh, notice that I wrote pi instead of x. I'm trying to see if you're paying any attention right there. So this is 2y squared minus 2x squared over y, right? Okay, why don't we set that equal to 0? Which just tells you that y squared is equal to x squared, hey? Well, we still have two variables, right? How do we get out of this pickle? Do you remember so many of this is a systems of equation? And this is another equation. That point xy here needs to be on that curve. So it has to satisfy this in order to be maximum. It has to satisfy this in order to be inscribed in that semicircle. You get it? Okay, let's substitute that here. So we have 2x squared is equal to r squared. And that tells you x is equal to plus or minus r over square root 2. But then plus or minus would be that side, so it's the same thing. So let's just keep plus. Then your y, well, looking at this equation right there, y should be the same thing, positive only this time, and your maximum area is 2 times x times y. That's r squared. Now, are you surprised by that answer? R squared? Does that look like R squared to you? Okay, this, if you're taking SAT, well, SAT's no, SAT 2, watch this. I'm gonna draw that line. I'm gonna just draw it with, forget it. I'm gonna draw it this way. Watch this. Change the color so you can see it better. Okay, let's take a look at this. This area is exactly same as that thingy. This area is exactly same as that thingy. And this is R, isn't it? So yeah, we have R squared. How about that? But yet there is another way to do this. And the other way is this. I'm gonna copy that thing and paste it down here and start this problem over. Okay, another way is parametric. I know you hate parametric, but watch this. I'm going to draw this line right here, and that's R, and our parameter will be that theta. Then our X is R cosine theta, and our Y would be R sine theta, wouldn't it? So let's restart. So A used to be 2xy. Now substituting these two things in, so we have 2r squared sine theta cosine theta. Not that we don't know how to differentiate this with respect to theta, but it's something, you remember that identity quiz? Now you can do this with ease. That's so much prettier to differentiate now, isn't it? So we can differentiate this. R is constant, remember, don't be using product rule here. So we have R squared cosine 2 theta, and then chain rule 2. Now let's set that to 0. Then what that means is cosine 2 theta is equal to 0. That means 2 theta is equal to 90 degrees. That means theta should be 45 degrees. How about that? That's beautiful now, isn't it? Then our area, of course, when theta is equal to 45 degrees, going back up here, yeah, we knew that maximum value of sine is 1 already, right? But plug it in if you want to, then we get R squared. Same answer, but a lot prettier. Running a can, right? Cylinder. Let's just draw the can, right? I mean, I have this writing thingy, so why don't I draw it? So this can will look like this. That's terrible. I don't know why I'm so... And my writing device is falling apart. Perfect timing, right? Really? Let's say this is a can, right? Okay, and then we are supposed to put 1000 cc, cc meaning cubic centimeters. Okay, now, and then total amount of aluminum, which is surface area, right? Can is thin shell, so amount of aluminum is this. Okay, now, and then, what kind of ratio we should have to H to R, and let's remind yourself, H is this one, and then R is this one, right? The ratio H to R in order to minimize the use of aluminum. That's why the cans have certain ratio. You know what I'm saying? You don't want it to be too skinny, you don't want it to be too fat, unless it's tuna. For some reason, tuna cans are fat. I guess that taking tuna chunk out of the can and you don't want to break everything. Okay. And then they have a reason. Instead of whatever, it's like, I guess this top and bottom part is more expensive or whatever. They have a reason to believe this is their mother. So we're just given this to use. Okay. Okay. So if I have my function a to be 8r squared plus 2 pi r h, and then you notice that this has to do with the base area and this has to do with the lateral area. You know what I'm saying? Okay, now this is not two independent variables, right? At the moment, this thing looks like multivariable calculus, doesn't it? But they are not two independent variables, so I'm going to move it over here. We need to find the relationship between R and H, so we can replace one variable, right? And this thing, they are not two independent, so they are dependent variable. We need to find that dependency, and we get it out of this statement. The volume has to be 1000 cc. So volume is pi r square base area times height, isn't it? And this needs to be 1000. Let's eliminate h. That sure looks easier. So h is equal to 1000 over pi r squared a. Say yes. And let's plug it in here. So we have 8r squared plus 2 pi r times 1000 over pi r squared. Good. Okay, simplify. I usually skip this part in previous years, but on this distance learning, I find myself babying you a lot more. Is that a good thing or bad thing? Do you feel insulted if I baby you like this?
It's a good thing.
Why is that a good thing? Is it -1 like that? Okay, all you babies. Do you see why that's -1, or do you want me to put it 2000 over r, and then that is equal to, okay, now we can take a derivative, dA over the r, and that is 16r minus 2000 r -2, right? Say yes. Okay, now we can set it equal to 0. That means, can I at least do this like 16 or wait. Can I at least do this much? And then r cubed is equal to 125 if you divide 16. Therefore, r is equal to 5, right? Let me push this thing down a little bit. Therefore, r is equal to 5. And h that goes with it, plug it in here, right? Then you have 40 over pi is what you're supposed to get, at least according to Dropbox note. So this is the maximum, the dimension that gives you the maximum. You get it? But they ask for the ratio. I'm going to do ratio over here. So h to r, right? So this thingy over that thingy. So that is 8 over pi. How about that? And then I'll just give this as well. This is a habit. Minimum, which is a at 5. And then that will be 600. How about that? But in this case, this is your answer. Question before I move on? Okay, let's move on. Inscribing triangle. This is a calculator problem, but we'll do the setup and then we'll just rely on the calculator. Okay. Now, area in this case, I'm going to call this thingy x and this thingy y. So that this coordinate right there is xy. You know what I'm saying? So I have 2xy, right? But what is my y? Well, my y is given right here. You get it? Oh, so that's easy. We don't really have to find the relationship because it's given to you readily available right there. So we have 2x times 4 cosine 1/2 x. You know what I'm saying? So we have 8x cosine x over 2. Derivative. Now this is a product rule. So u prime 8 cosine x over 2 and derivative of cosine. You think this is, I'll just write it, plus 8x and then negative, so negative changes to minus sine x over 2, but the chain rule, right? We have to differentiate this thingy, which gives you half. Good. Say yes. Now we set that to 0. That means, now this is like, how do you solve this? You can't. Right? So doing it with a calculator. So my x should be 1 point, wait, let me copy it from the note. 1.720667, and then y that goes with it, of course, is 2.608739, and the area, the maximum is, you notice that I'm putting 6 decimal points, 6 decimal places. This becomes your max. How about that? Good.